بسم الله الرحمن الرحيم. الصلاة والسلام على محمد وعلى آله الطاهرين. السلام عليكم ورحمة الله. Mrs. Dalal, Mr. Ahmed, Mr. Oday, Mr. Yasser, Mr. Tamimi, Mrs. Zainab, and Mr. Ahmed, and Mrs. Maryam. Excuse me because of this delay. That's right. We completed 3 parts, okay? The last part 1, part 2, part 3, I say to you. Part 1 was unitary transforms, for example, DFT, DCT, DWT, and DHT and KLT, okay? Some transforms. Discrete Fourier transform, discrete cosine transform, discrete Hadamard transform, and etc. Part 2 was image enhancement, for example, histogram, spatial filtering, etc. Part 3 was image restoration, okay? And this is part 4. This session is starting of part 4. Part 4, as we said lastly, was about image comparison, okay? And this time, in this session, we start with fundamentals of image comparison. That's right. This file is digital image processing, image comparison, and the first time image comparison fundamentals. Okay. Go ahead. What's about comparison? New techniques have led to the development of robust methods to reduce the size of the image, the size of the video, or the size of an audio file or audio data. Okay. Such methods are extremely vital in many applications that manipulate and store digital data. You know that these times all of we and all of us are familiar with these items, okay? In our system, Salam, Mr. Abbas. These methods of comparison are all around of us in our, for example, phones, in our laptops, and etc. For image, for video, for audio, and for files. Informally, we refer to the process of size reduction as a comparison process, okay? We will define this process in a more formal way later in other slides and in other sessions. On the architecture front, it's not feasible to put sophisticated comparison processes on a relatively low-cost single chip. For example, by some cents in a or some dollars, okay, in a small chip. You can, for example, run some comparison processes, or in DSPs, in microcontrollers. That's right. This has spurred a great deal of activity in developing multimedia systems for the large consumer market. As I said, around all of us, in our systems, in our phones, in our laptops, etc., you run a huge number of applications. Most of them are using, for example, comparison methods. That's right. Go ahead. Comparison is a process intended to yield a compact digital representation of a signal, okay, or a compact size, or a small size. In the literature, the terms source coding, data comparison, bandwidth comparison, and signal comparison are all used to refer to the process of comparison. Okay, source coding, data comparison, bandwidth comparison, better bandwidth usage, signal comparison, all of them. These are good keywords for searching, for example, in image comparison or data comparison, okay, or naming the whole process of comparison. In the cases where the signal is defined as an image, a video stream, or an audio signal, the generic problem of comparison is to minimize the bitrate of their digital representation. Minimizing bitrate, okay, or in the same time I can, for example, transfer more data. There are many applications that benefit when image, video, and audio signals are available in compressed form. And very important, without comparison, most of these applications would not be feasible. For example, in online streaming, if we didn't have, for example, comparison, for example, this online class wasn't, for example, feasible. Or transferring some video films over the internet, maybe some not be feasible, and other huge set of examples. Next slide. Why we can compress the signals, why it's possible? There's considerable statistical redundancy in the signal, or correlation between, for example, pixels and frames, and etc. One, within a single image or a single video frame, there exists significant correlation among neighborhood or neighbor samples. That's right. For example, this area, all of them maybe have the blue color. This is a good correlation. Or a good redundancy. That area, for example, all of these pixels have, for example, green color. A good correlation between this huge number of pixels and this area. Within a single image or a single video frame, there exists significant correlation among neighborhood or neighbor samples. This correlation is referred to as a spatial correlation. A spatial or position, a spatial. For example, this point, this area, this is a spatial correlation between pixels. Another one, two, for data acquired from multiple sensors, such as satellite images. This sensor, some sensors. There exists significant correlation amongst samples from the sensors, are familiar with each other, the output of these sensors. This correlation is referred to as a spectral correlation. TAFE, a spectral frequency, a spectral correlation. And three, for temporal data, such as video, temporal, this time, frames of video. There is significant correlation amongst samples in different segments of time. This frame and this frame. For example, in between these two frames, a large correlation between these pixels. This is referred to as temporal correlation. Thus, we have at least three correlations: a spatial correlation between these pixels in this frame itself, or in this figure, a spectral correlation from correlation between pixels from some different sensors, spectral, and temporal. For example, in video frames, this frame and the next frame and the next frame, maybe this area isn't changing, and is nearly constant. This is a temporal correlation. Important. There is considerable information in the signal that is irrelevant from a perceptual point of view. For example, if this frame is very different from the last and the second and the next frames, maybe this frame is very important, and has a huge information in it, is different from the other frames. For example, you are seeing a video file. In some seconds, for example, a frame is showing important. Please refer to this message, for example. Okay, this frame is different from the previous and the next frames, and maybe this frame has some important data in it, and without any correlation with other frames. That's right. Some data tends to have high-level features that are redundant across space and time. Thus, the data is of a fractal nature. In some situations, for example, maybe we have some fractal information, okay, that can be repetitive in some times over the frames. That's right. Okay, go ahead to the next slide. Oh, again, this is the slide number 5. Okay, and go ahead. 6, 4. Alright, okay, but this isn't good. Okay, I stop sharing and go for my screen for 5. Stop sharing, share my screen. You see my screen. What about it? Part 4. Part 4. Image comparison. Here. Image comparison fundamentals. This was where you can compress the signal, and this is the page 1, page 4 or 5. Okay. Why do we need comparison standards? Why do we need the comparison standards? Okay. For example, JPEG, etc. I enlarge it. Multimedia information comprising image, video, and audio has become just another data type. Okay, for example, beside the other files, another data type. This usually implies that multimedia information will be digitally encoded so that it can be manipulated, stored, and transmitted along with other digital data types. Okay, all of them should be working with each other. What do you say? Salam, Masa Ali. Salam, Allah Salam. Okay. For such data users to be pervasive, it's essential that the data encoding is standard across different platforms and applications. Okay, all of them should be working with each other without any hardness. Okay, thus we should use the same standards over all of the vendors all around the world. Okay, or a huge percent of them. This will foster widespread development of application, and we will also promote interoperability among systems from different vendors. When we use the same standard, some new applications and new hardware, for example, can be created, and from new vendors and old vendors, okay, and can be working with each other. Furthermore, standardization can lead to the development of cost-effective, because of mass production, okay, and a huge number of users, because of this is cost-effective. Development of cost-effective implementations, which in turn will promote the widespread use of multimedia information. As I said, a mass production, okay, and for example, millions and 10 millions and 100 millions and milliards, okay, billions users, for example, for some data. This is the primary motivation behind the emergence of image and video comparison standards. This is a necessary item, okay, in manipulating images and videos. That's right. I stop sharing my video, my screen, and go to again sharing the document for better performance. That's right. We said about this slide. Thus, go for the next one. Some examples. Examples of data comparison. Example 1. Let us consider facsimile or fax. Okay, facsimile image transmission. In most facsimile machines, the document is scanned and digitized. Okay, old machines, fax. Typically, and for example, 8.5 by 11 inches page is scanned at, for example, 200 dot per inch. Okay, DPI. The number of individual dots that can be placed in a line within the span of, for example, 1 inch. DPI, dot per inch. Thus, resulting in, for example, near 4 megabits. Okay, 3.74 megabits. For example, one page, one scanned page for faxing. Okay, for transmitting over fax. And transmitting this data over a low cost, for example, 14.4 kilobits per second modem, old modems. Okay, these examples are old, would require, for example, more than 5 minutes, 5.62 minutes. That's right. Without comparison, about 6 minutes. But with comparison, the transmission time can be reduced to about 17 seconds, not minutes. Okay, 17 seconds. A very good performance. Okay, a very good comparison rate. About 6 minutes, about 20 seconds. Okay. This results in substantial savings in transmission costs, transmission times, then transmission costs. Okay, or price. Another one, example 2. Transmission costs for operators. Okay. Example 2. Let us consider a video-based CD-ROM application. CD-ROM. Again, old CD-ROMs, okay? Not DVD-ROMs for these times. Full motion video at, for example, 30 frames per second, and for example, 720 by 480 resolution. That's right. Generates data at, for example, more than 20 megabytes per second. More than 20 megabytes per second. At this rate, only 31 seconds of video can be stored on, for example, a 650 megabyte CD-ROM. Okay, over a CD-ROM you can save about half of a minute of a video file. That's right. But comparison technology can increase the storage capacity over that same CD-ROM to more than 70 minutes. Okay, about 74 minutes. Half of minutes, 70 minutes. Again, more than 140 enhancement rate. Okay, comparison rate for VHS grade video quality, for example. That's right. What is same as a bus? Okay, that's right. Okay. A good slide, for example, for some sense, okay, for some applications of image, video, and audio comparison. I enlarge it again. For example, application and data rate. Okay, uncompressed data rate and compressed data rate. For example, for voice, 8 kilo samples per second, and each sample 8 bits. Okay, 8 bits per sample. Without compressing, you need a 64 kilobits per second of baud rate. Okay, but for compressed one, you need only about 3 kilobits per second. Okay, 2 to 4 kilobits per second. For example, 3 times of performance. Okay, or for example 16 times of performance. Very good. 64 kilobits per second, or 2 or 3 or 4 kilobits per second. Another one, a slow motion video, 10 frames per second. Okay, and frame size 176 by 120, and 8 bits per pixel. Okay, a low quality, 8 bits per pixel. Without comparison, more than or about 5 megabits per second. 5 megabits per second of data rate, okay, over your line. But with comparison, a huge performance, okay, 8 to 16 kilo, not mega. 5 megabit per second, 16 or lower than 16 kilobit per second. That's right. Another one, audio conference, 8 kilo samples per second, and each sample 8 bits. Okay, again 64 kilobits per second for compress. Again in this item, 16 to 64 kilobits per second is the same, not good performance. Okay, about 1 to 4 better performance for audio conference. For video conference, 50 frames per second with this frame size. For example, 300 by 200. Okay, and 8 bit per pixel. More than 30 megabits per second for uncompressed, and about 64 to about, for example, 800. Okay, kilobit per second, megabit, and mega kilo. Digital audio with this sampling per second, 44.1, and good quality. Okay, 16 bits per sample, 1.5 megabit per second for this one, and about is the same. 1.28 to again 1.5 megabit per second. This item and this item is the same because of needing good quality. For example, video file transfer, for example, for 15 frames per second. Okay, and with this frame size, 300 by 200, for example, and 8 bits. Again, this item, again about 30 megabits per second, and about 30 or 40 kilobits per second. Okay, and about 1000. No, about 1 or 100 hundredths performance. Digital video on CD-ROM by 30 frames per second, but this frame size and this samples about 60 megabits per second, and compressed about 2 to 4. Okay, 1.5 to 4 megabits per second. A good again performance. Broadcast video for 30 frames per second, and this size and this bits per pixel, 8 bits per pixel. about 250 megabit per second for uncompressed, and about 3 to 8 megabit per second. Again, very good. And HDTV, high definition TV, okay, television, for about 60 frames per second, and from frame size of 1020 280 by 720, okay, and again 8 bits per pixel. 1.33 gigabits per second for uncompressed, gigabit per second, okay, about 1 gig, but 20 megabit per second, a performance of about 50, okay, it's very good, very good. Some good examples, okay, for some good sense for videos and pictures. Go to the next slide, but first reducing the size. That's it. Learning comparison system. For example, this is input, this is channel for transmitting, and this is output, okay. Here, digital image, video, and audio file, okay. This is all file or source data. This is encoder, previous to transmitting to channel, okay. Named encoder, and the encoder consists of source coder and channel coder, okay. For example, source coder means comparing video file, for example, okay, and channel coder, for example, modulator, okay. Modem means modulator, demodulator for channel, okay. Channel coder, for example, using some modulation schemes, for example, analog modulation, digital modulation, etc. PCM, some modulations, okay. This is our speak. Source coder, comparator, okay, compressor. This is channel. After receiving from channel, for example, this is your fiber, optic fiber, or this is a satellite channel, okay, or this is a LAN cable. That's right. This is in receiver. This item encoder is for transmitter, for transmission side, and this decoder is for receiving side. Again, this is demodulator, okay, demodulator, channel decoder, and this is source decoder, okay, or unzipping, uncompression, okay, transferring to the previous or the first file. Again, digital image and video and audio. That's right. Next slide. What about source coder or zipper, okay, compressor, and about a very important item named comparison ratio. Comparison ratio. To how many rate this, for example, zipper can zip or compress or file. The source coder performs the comparison process by reducing the input data rate to a level that can be supported by the storage or transmission medium. For example, you have a CD-ROM, okay, or you have a bandwidth for your channel, okay. Your compressor should prepare your data for transferring our this channel, but predefined data rate, or for storing our this CD-ROM, our this DVD-ROM, or this RAM, or this ROM, etc. Okay, for storing or for transferring. The bitrate output of the encoder is measured in bits per sample or bits per second. How many bits per sample, okay, or how many bits per second? The output of this encoder. For image or video data, a pixel is the basic element, That's right. Thus, bits per sample is also referred to as bits per pixel. Okay, how many bits you need for example, for transferring a single pixel? Bits per pixel, okay, or bits per sample. In the literature, the term comparison ratio, CAR, comparison ratio, is also used instead of bit rate. Okay, instead of using bit rate, you can say a better one. What is the comparison ratio? For example, 20, 50, 100. It's better. More number, a larger number is better. Okay. It's also used instead of bit rate to characterize the capability of the comparison system. An intuitive definition is here. Comparison ratio, or CAR, is source encoder input size to source coder output size. Okay. For example, 1 meg over 20 kilo. Okay, is, for example, about a CR of 50. That's right. 1 gig over 1 meg, a CR of 1000. A good performance. Okay, 1000. In this slide, this item divided to this item. For example, here, 1.3 gigabit per second, or about 1300 megabit per second, to 20 megabit per second. Okay, is about 65. About 65 ratio is very good. Another one. Again, for comparison ratio. Excuse me. The definition of comparison ratio is somewhat ambiguous and depends on the data type and the specific comparison method that is employed. Okay, not the same sense for different applications and different hardwares and different data. Okay, depends on the data type and the comparison method. Okay, for a still image, size could differ to the bits needed to represent the entire image. How many needed bits needed for example, all of this frame, all of this picture? Okay, for example, 1 megabits, 100 kilobits, etc. For video, size could refer to the bits needed to represent one frame or video. Okay, for picture, all pixels of this picture. For video, size is all bits needed for one frame of this picture. Many comparison methods for video do not process each frame of video. Okay, some methods. Hence, a more commonly used notion for size is the bits needed to represent 1 second of video. Why? Because, for example, you have 1 frame per second. No, 10 frames per second, 15 frames per second, 30 frames per second, 60 frames per second. Okay, this times 240 frames per second. Not the same frames per second. Okay, thus this is better, maybe in some sense. Maybe the size is the bits needed to represent 1 second of video. How many frames? Okay, 1 second of video. How many bits is needed? Okay. because you don't be tired and listening me, please type 1 if you are ready in the class. Okay, Mr. Abbas, are you ready? Mr. Abbas, Mr. Abbas, if you are ready, please type 1. Okay. Mr. Ahmed Qasim, please type 1. Mr. Ahmed Qasim, are you in the class actively or not? No, Mr. Yasser, you don't know. You don't type. Mr. Ahmed Qasim. Okay, Mr. Ahmed Qasim, 1-1. That's right. Mr. Abbas again. Mr. Abbas. Okay, that's right. Okay, Mrs. Dalal. Mrs. Dalal, are you ready in the class? Ahsan. Oh, مخلصين. Mrs. Dalal can speak in Persian. Okay. شما میتونید فارسی صحبت کنید. دم شما گرم. Okay, Mr. Hamid. مستر حامد، مخلصیم خانم دلال، مخلصیم. انشالله زیارت میکنم خانم دلال. مستر دانشگاه، مستر حامد. اوکی، مستر حامد. مستر Uday, ای الله. مستر Uday, that's right. اوکی. مخلصیم. مستر Uday انشالله إن شاء الله السلامة والصحة أنت زوجتك مخلصين. مستر عباس ربي يحفظك. أو مخلصين. نحن مخلصين مستر عباس، نحن مخلصين. أوكي مستر حامد، أهلا وسهلا. مستر حامد الآن في إيران. أيوة الله. Type for me previous to the class. He is in Iran from yesterday. أهلا وسهلا بك في إيران. إن شاء الله أنا بخدمتك في جامعة. أوكي. مستر ياسر تميمي. مستر ياسر. أوكي. Good. Mrs. Zainab. Mr. Ahmed. That's right. أنا أيضا إن شاء الله أنا بخدمتك إن شاء الله في الجامعة. Okay, Mrs. Zainab, that's right. Mr. Ahmad. Mr. Uday. كلكم في إيران؟ Mr. Uday, Mr. Salam, Mr. Ham, كلكم في إيران؟ Mr. Uday الآن؟ أي جان، أي نعم، أيوة الله. إن شاء الله أنا بخدمتكم في الجامعة في العراق الآن. أيوة الله. أوكي، that's right, Mr. Ahmad. Mrs. Maryam, are you in the class? Mrs. Maryam. Okay, that's right. This was a break, okay, for continuing. And أهلا وسهلا to Uday, Mr. Hamid, and Mr. Salam. Inshallah, أنا زايركم for example for tomorrow, for other times, other days. That's right. Continue. Inshallah. أنا باخد بالكم. Comparison requirements. Okay, inshallah. Comparison requirements. A specified level of signal quality. Okay, this constraint is usually applied at the decoder, not encoder. At receiver, we need a good quality. Okay, for example, for sensitivity of receiver. Okay, or for equality for our sense, human sense. Signal quality for receiver side, for decoder side. Implementation complexity, okay? Complexity. This concept is often applied at the decoder again, at receiver again, okay? And in some instances at both the encoder and the decoder. But in most of senses, in encoder, not decoder, okay? Both of them. But decoder or receiver is very important. For example, for broadcasting. Okay, I have a single transmitter, for example, the transmitter tower. Okay, I have a single transmitter for example, a whole of city. For example, a BTS, okay, or a tower. But a huge number of receivers, for example, in the home of users, or for example in the pocket of users, okay, in their phone. Thus the receiver complexity or the receiver cost is very important, okay, for all of users. Not one item add receiver. One item add receiver can be very complex and no problem, okay. Another one, communication delay. Communication delay time. This constraint refers to the end-to-end, okay, end-to-end delay. This constraint refers to the end-to-end delay from starting to receiving, okay, and is measured from the start of encoding, start of comparison process, okay, a sample to the encoding sample to the or a file to the complete decoding of that sample. For example, receiving it, okay, and unzipping it and ready for use, okay, for example, for seeing, for hearing, etc., for storing. Note that these constraints have different importance in different applications. For example, in a two-way teleconferencing system, okay, audio teleconferencing system, the communication delay might be the major constraint, okay, because delay between our speak is very bad and a bad sense, okay. Whereas in a television broadcasting system, signal quality and decoder complexity might be the main constraint, not delay, okay. For example, from the transmitter tower to our home be about, for example, 5-second delay. No problem, okay. But for example, for quality at my television is very important, or complexity of my set-top box, for example, okay, lower complexity tends to lower cost, and this is very important for me for broadcasting television, okay. But for teleconferencing, okay, in audio conferencing, for example, not second but milliseconds, okay. For example, 10 milliseconds may be bad, 10 milliseconds may be bad, okay. That's right. In each case, maybe some of these constraints is has more importance. Next slide. Don't be tired, inshallah. Lossless compression. We said in the last sessions we have two methods, lossy and lossless, okay. For videos and pictures, lossy may be good. Lossy have a better compression rate, but lossless is, for example, for file data, okay, for digital data. That's right. Lossless comparison trade-offs. For example, we can categorize in three categories: coding efficiency, coding delay, and coding complexity. Coding delay, we said end-to-end delay, okay, or time. Coding efficiency, for example, efficiency ratio of comparison, CR, comparison ratio, 50, 70, 100, 20, what is the ratio of comparison? performance. And coder complexity. For example, memory requirements, how many gigabit or gigabyte of memory this times. Power requirements, how many milliwatts of consumed power for example, this comparison and decomparison. Operations per second, okay? How many, for example, flops, floating point operations, okay, per second. These items for complexity. Gigaflops, megaflops, other items. But lossy comparison. Lossy comparison has more applications, okay, for video streams, for example. The majority of the applications in image or video data processing do not require that the reconstructed data and the original data are identical in value. For example, some difference between them is acceptable, okay? Not data, this is image, this is video, okay? Thus, some amount of loss is permitted, is allowable, okay, مجاز, in the reconstructed data. A comparison process that results in an imperfect reconstruction is referred to as a lossy comparison process. What is a lossy comparison process? Permitting some differences between the origin file, for example, video file, and the resulted unzipped version. Okay, some differences is allowable, is mojaz, okay, is permitted. This comparison process is irreversible. Okay, that means you can't repeat this process. For example, from the original file, zipping, then unzipping the result. Again, zipping and unzipping this one to another one. This one to another one is degrading the quality of the original file. Okay, irreversible. In practice, most irreversible comparison processes degrade rapidly the signal quality. Okay, when they are repeatedly applied on previously decompressed data. Not permitted to repeating this process, okay, one by one. The choice of a specific lossy comparison method involves trade-offs along the 4 dimensions shown in figure, next figure, in the next slide, okay. For lossless, we have 3 items, okay. For lossy, we have 4 items or 4 dimensions, okay. These 3 items and this next dimension. Go back and this item. Due to the additional degree of freedom, namely, I say this item. We had and we have these 3 items for both of them. Coding delay, coding efficiency, and coder complexity is the same for lossy and lossless. Okay, but for lossy, this item or this dimension is only for lossy. Signal quality. Why? Because we said these 2 items aren't the same. The original one and the reconstructed one. But if these aren't the same or have some differences, what is the quality of reconstructed? Okay, that can be represented in these items. Bit error, BER, bit error rate or bit error probability. How many differences in sometimes between the original one and the reconstructed one, okay, or SNR, signal to noise ratio. Okay, what is the dividance between signal energy and noise energy? Okay, and mean opinion score. What about the users and human senses? Okay, they like this compressed and uncompressed or not? What's their sense? It has a good quality or not? Okay, mean opinion of users. Okay, to do the additional degree of freedom, these 4 items, namely in the signal quality, a lossy compression process can yield higher compression ratios, okay, than a lossless compression sham. For reaching better performance in compression, okay, or compression ratio, lossy is better. But for better quality, lossless is better. That's right. That's right, inshallah. Okay. And go to the next slide. Only 3 other slides and about 15 minutes. Okay, that's right. Lossy compression and signal quality and SNR, signal to noise ratio. My hand is, for example, some pain. I have some pain in my hand. This term is often used signal quality. This term of signal quality is often used to characterize the signal at the output of the decoder. Decoder was at receiver. Okay, the quality. There is no universally accepted measure for signal quality. Maybe I say this is signal quality, you say this is signal quality. Okay. One measure that's often cited in the signal to noise ratio, one good measure is the signal to noise ratio. Okay. Signal to noise ratio is a good item, good parameter for all of us, for example. Okay, which can be expressed as this item, signal to noise ratio in a logarithmic form. Encoder input signal energy to noise signal energy. Signal to noise ratio, signal energy to noise energy. Okay, this is a good parameter for all of us. The noise signal energy is defined as the energy measured for a hypothetical signal, that is the difference between the encoder input signal and the decoder output signal. Okay, and high SNR, not OR, high SNR values do not always correspond to signals with perceptually high quality. In some senses, maybe you have a good SNR, but not a good quality. Okay, this is not as sufficient. Okay, this is a necessary, for example, a necessary parameter, SNR, not as sufficient. Maybe you have a good SNR, but you don't have a good quality. Okay. But some important item. ياسر أحمد, what you typed? تأخير كان لدي مشكلة في Mr. Yasser, this time is quality good or not? Mr. Yasser, if quality is bad, I can turn off my camera. All of you, quality is good or not? This time we are going about signal quality, okay? And some of you may be telling good, some of you telling bad. Quality is good this time? Inshallah is good. You are not answering me. That's right. Oh, okay, Mr. Yasser, okay. خوب هست صدا خوبه، تصویر خوب نیست؟ خانم دلال؟ خانم دلال آها الان هر دو خوبه یا فقط صدا خوبه؟ خیلی خوب، بسیار نیست، بسیار نیست. خانم دلال چون شما فارسی متوجه میشین به جای یه اگه شیفت ایکس تایپ بکنین درست میشه، مشکل پیش نمیاد. یه بار دیگه بنویسین خیلی خوب، به جای یه شیفت با ایکس، شیفت ایکس بنویسین خیلی خیلی خوب. هر جای یه خواستیم بگین شیفت ایکس تایپ کنین، یه بار تایپ کنین. Please type. بنویسیم مثلا خیلی یا خیر، به جای یه شیفت ایکس بنویسیم. تلفن؟ متوجه نشدین چی گفتم؟ خیلی خوب، بی خیال. That's it. Again, أنا قلت, okay, Mrs. Dalal, قلت, please type Shift X instead of type yeah. In Adobe Connect, Shift X, Shift plus by X instead of yeah. For example, you are typing خير, ليل, okay? Instead of ya, please type Shift plus by X. That's right. Last comparison, signal quality, mean opinion score. This time, what about another one? For signal quality, we said about SNR. Okay, one parameter for quality was good but not sufficient. Okay, parameter was SNR, signal to noise ratio. But another one, we can use mean opinion score. What our users say, quality is good or not. For example, this time I'm asking you, Mrs. Dalal, Mr. Yasser, all of you, for example, my audio is good or not, my video is good or not. Okay, another measure for of signal quality is the mean opinion score, opinion of our users. Okay, opinion means, for example, view. Okay, where the performance of a comparison process is characterized by the subjective quality of the decoded signal. Subjective quality in point of view of all users, okay, and mean of all of users, not only one person, all of them, what they saying about the quality is good or not. For instance, a 5-point scale, such as, for example, very annoying, very bad, very annoying, bad, slightly annoying, some bad, good, for example, perceptible, okay, or but not annoying, okay, and imperceptible, okay, bad, perceptible, not perceptible, okay, might be used to characterize the impairments or levels of distortion in the decoder output. For getting feedback from our users, I asked them this time, the quality is good or bad? Very bad, bad, so bad, very good, okay. In higher lossless or lossy comparison systems, okay, both of them, the quality of the input data affects the comparison ratio, the quality of the input data, okay. Better input file tends to more ratio of comparison, okay. For instance, acquisition noise for capturing the video file. For example, in your camera, in your laptop, okay, or your microphone in your laptop. If didn't have any noise, it's very good. But if your captured file had some noises, okay, this is bad, and you can't use a good comparison ratio. Okay, for instance, acquisition noise, data timing errors, these items: acquisition noise, data sampling timing errors. For example, not the baud rate, jitter, or named jitter, okay, or لغزش. I don't know what is in Arabic. Differing the sampling between items, okay, this is jitter. Acquisition noise, data sampling timing errors, and even the analog to digital conversion process, okay. Maybe your A to D is bad, A to D, a lower bits A to D, for example 8-bit A to D, 4 bits A to D, or vendor of A to D, for example, okay. And even the analog to digital conversion process affects the signal quality for input signal, okay, before comparison, affects the signal quality and thus reduces the spatial and temporal correlation, okay. Some comparison schemes are quite sensitive to the loss in correlation and may yield significantly worse comparison in the presence of noise. That's it. Noise is bad, okay. A bad A to D again is bad, and some jitters in sampling again is bad. A bad clock pulse, for example, your system is bad. These items affect your performance of your compressor, okay, or comparison scheme or system. And the last slide, okay, the last one, and this is the overall time. Issues in comparison method selection, okay, lossy, lossless, or other items. Ratio, lossless or lossy, which is better? We said for example, good quality, lossless is better. For example, for transferring some important information, maybe for example for files, okay, important information, you use lossless processes, okay. But if the performance or quality isn't, the image quality isn't, for example, of importance, but baud rate is or comparison ratio is has more importance, you use lossy processes, okay, or lossy schemes. Coding efficiency, about source coding, okay, not channel coding. Efficiency of coder or compressor, okay. Variability in coding efficiency. Variability means repeatability, okay. Variability for example, some different files, for example, or for example, reconfiguration of this system, or working in some different situations, some temperature, some days, etc. Variability in coding efficiency. Resilience to transmission errors. For example, what's the performance of your system for bit error rate of channel, okay. If my channel was bad or has a bad quality, okay, or this system is good for it or not, this comparison system is good or not. Complexity trade-offs. We had three trade-offs for lossless, and 4 trade-offs, 4 category of trade-offs. Okay, for lossy, we should investigate these trade-offs. Okay, nature of degradations in decoder output in the receiver. What degradations are there? Okay, data representation. What's the representation? For example, in office, in home, by video, by audio. What about it? Okay, multiple usage of the encoding decoding tandem. Multiple usage. Okay, using over and over. Interplay with other data modalities such as audio and video. Working and interaction between these, for example, files. Okay, and interworking with other systems, or system with another system from another vendor. Okay, and another system in the whole of DSP, digital signal processing. These items, these issues should be, for example, investigated for using a good comparison method. That's right. And the time is over, exactly this time. Time is 7 in Tehran time. That's right. This was the last slide, 17th slide for this fundamentals. Okay, for this introduction for part 4 of our lecture. Part 4 was and is about image comparison, okay, and video comparison, etc. The next time we continue for part 4 for image comparison. Is there any question, my dears? Is there a question? أنا بخدمتكم. No. That's right. Okay. If there's any question, again, I put this file over the LMS. That's right. If there's any question, I type. Again, I say أهلا وسهلا to Mr. Odey, Mr. Ahmed, and Mr. Salam. إن شاء الله أنا أزوركم as soon as possible. Okay. This time, this week, next week, etc. Each time was good. Okay. أنا type خدا حافظ همگی. خدا حافظ همگی means الله يحفظكم جميعا. في الله في الله. Okay. That's right. خدا حافظ.